Good morning, very good morning. So wait for a minute, then we'll start the class. Wait for 1 minute. 1 minute. I'll start. Sorry for the inconvenience. Okay. So yesterday class we have finished about like what we call Legender's differential equation, and we have seen different properties like orthogonal properties we have seen, and as well as the recurrence relations also we have seen in the last class. So today what I am going to do is I'm discussing about Bessel's differential equations. So in this Bessel's differential equation also we have to solve for the equation, and we have to get the solution, and also we will be having the recurrence relation in this Bessel's differential equations. Okay, so that we'll see today here. Right. So for that purpose, I'll share the I'll start sharing the screen to take this Bessel's differential equation. So if you have material with you, you take it to your material, and we'll go through that one also. Okay. Okay. So now, are you able to see this Bessel's differential equation? Any one of you? So that we will start respond.
Yes, sir.
Yes, sir.
Yeah.
Yes,
Right. So as we have seen the Legender's differential equation, here also we have the Bessel's differential equation. So this Bessel's differential equation, it has been so this Bessel's differential equation, which we have here, it is we can write it as x square d square y by dx square plus x dy by dx plus x square minus n square into y is equals to 0. Okay. So this one we call it as a Bessel's differential equation we have. Now what we'll do is we will divide this equation with x square on both sides. Okay. So we'll divide with x square on both sides. So here, 1 minute. So if you divide with x square on both sides, so what you are going to get is we'll get it as d square y by dx square, because x square will get cancels, plus in the second term we are going to get it as 1 by x dy by dx, and in the third term here, the third term, 1 minute here, here we have. So here we will write it as 1 minus n square by x square we can write. Okay. So here, this one. Okay. So we can write it as a 1 minus n square x 1 minus n square by x square, because we have divided with the x square, so that this equation, whichever we have the differential equation, will leads to this equation. This is what we can write. Then we have to take the solution for this equation. That is, we have to write the solution for this equation, which is called it as a Bessel's function of order n. We are going to be called. So therefore, the solution for this equation, we can write it as the following manner. See here. See here. So we can, 1 minute, I can erase this. Right. Now, if you write this solution for this one, that equation can be written as y is equals to this one, that is x power k a0, that is x power k into plus a1x plus a2x square, and so on. We can write like up to ar x to the power of r, we can write here. So this entire equation, whichever we have, we can write in the form of summation, that is summation of r is equals to 0 to infinite. That means its values like a0, a1, a2, and ar we are going to be getting. So that values takes from r is equals to 0 to infinite, you are going to be taken. Then after, we can write this as ar x to the power of k plus r, we can write. Okay, ar x to the power of k plus r we can write here. So thereafter, here, this is the y, that is the solution for the Bessel's differential equation. We have been written as y is equals to summation of r is equals to 0 to infinite, and ar x to the power of k plus r we have been written. Now what we have to do is, in the equation, that is the Bessel's differential equation, we have like a y dy by dx is there. Okay, see here, if you see here, so we have the first order differential equation, differentiation, that is dy by dx is there, and d square y by dx square is there. So that what we have to do is, we have to differentiate this, the solution, whichever we have been taken, the solution which we have assumed as a y is equals to summation of r is equals to 0 to infinite, we have been taken, no? R is equal to 0 to infinite, x to the power of k plus r as the solution which we have been taken. So that is a y value. 1 minute. So this is the y value which we have been taken here. Okay. So this is the y value which we have been taken. So if you differentiate this equation, we are going to get it as a dy by dx. So summation of r is equals to 0 to infinite as it is, as we have seen yesterday's class, that is x to the power of n, x to the power of n minus 1. So therefore, we are getting it as ar as it is, we are writing x to the power of k plus r, differentiation is k plus r, okay, into x to the power of k plus r minus 1, you are going to get. So this is the first order first differentiation, that is dy by dx we have got. Next, we have to get this d square y by dx square also. So if you differentiate this above equation once again, this equation, if you differentiate, we are going to get the value of d square y by dx square we are going to get here. Okay. So this value we are going to get. The d square y by dx square. So once after getting these, what we call dy by dx as well as the d square y by dx square, These values we are going to be substitute in the equation, that is what we call the general what we call the differential equation, that is Bessel's differential equation. We have to substitute. So what is the Bessel's differential equation we have is, we have like a x square, sorry, d square by dx square plus 1 by x into dy by dx into 1 plus n square minus n square by x square into y. So first term is d square by dx square. So this value, whichever we have, this value which we have here, it is this one we have written here. Okay. So this d square by dx square value here we have written. Plus we have 1 by x into dy by dx. So we have dy by dx is this one. So we'll write dy by dx here. That is entire value. Plus we have a 1 minus n square by x square into y. So y value we have taken it as this one. Summation of r is equal to 0 to infinite ar x to the power of k plus r. So that is what we have written. So then after writing this, so what we are doing is we have to we have to simplify. That means we have to rearrange the terms. So in this, if you rearrange as a coefficient of x to the power of k plus r minus 2, one term we are going to get. Another term as a coefficient of x to the power of k plus r we are going to be get. Okay. So this entire two terms combined, and we have written x to the power of k plus r minus 2 coefficient as this one. And this entire term we have written as the coefficient of x to the power of k plus r as this one. So once after writing this one, simply what we are doing is we are rearranging again. That means here k plus r is there. So k plus r as it is we are writing. Here k plus r.
Sir, after add x equal to k plus r minus 2 after plus 1, sir.
Yes, yes. Which equation?
Excuse me, sir.
Somebody is who is getting voice of children. Please.
Sir, Abhishek is speaking, sir. Please explain x ke power k r minus
doubt. What doubt you have?
Excuse me, sir. Speaking, sir.
Yeah, please. You tell me your doubt.
Doubt, sir. X ke power k plus r minus 2 after plus summation of ar x equal to, sir.
This one.
Below, sir. Below, sir.
This one.
This one after x ke power k plus r minus r plus summation of ar.
Here plus should be there.
Yes, sir. So plus should be there, sir.
Okay. Yes, yes.
This is missing, sir.
Yes, yes. 1 minute. I'll tell. 1 minute. The term I'll tell. 1 minute. I'll calculate and I'll tell. Yeah, there it should be plus. So note it down your material. Here.
Okay, sir. Also, here, material is missing, sir.
Yeah, plus term is missing. Here. Here plus term should be there. I'll write here. Okay.
Okay, sir.
Term should be there. Even here also. Understand? Even here also sir. The plus term will be there, and as well as at this point. At this point also plus term should be there. Okay?
Okay, sir.
Right. So it is not there in your book, textbook, maybe that printing mistake.
Yes, sir. Also printing mistake, sir.
So
there is
plus term should be there. So finally, we can write the equation as this one. Understand? What we can write is this one. That is summation of r is equal to 0 to infinite ar k plus r whole square minus n square into x to the power of k plus r minus 2 plus here it should be there. I have written, no? You note it down in your material, all of you. If you have material, you make it correction in that there should be plus sign. So therefore, it will be summation of r is equal to 0 to infinite ar x to the power of k plus r is equals to 0. So this is the equation which we have. So now this equation, whichever we have got, equation 2.4, we will be calling it as a equation is an identity. Okay, equation is an identity. So if this is the equation is an identity, so what we have to do is the coefficients of various powers of x, that means x to the power of k plus r minus 2 coefficients, and as well as the x to the power of k plus r coefficient should be equals to 0. Understand? So whatever may be the coefficients which we are getting, maybe this coefficient and as well as this coefficient should be equal to 0. So first of all, we will equate the coefficients of x power k minus 2 here. Understand? X to the power of k minus 2. So in order to get x to the power of k minus 2, we will write r as r minus 1. We write. So here, if you want to get the x to the power of k minus 2, if you want to get this, r should be get cancelled. So what we have to do is in place of r minus we are going to write. So there we are writing it as 0. Yes. Someone is speaking. So do you have any doubt? Okay, anyhow. So here, in order to make the coefficients of x to the power of k minus 2, simply we have to put r is equal to 0 in this. So we are going to get a0 k square minus n square is equal to 0. We are going to get faster. And then what we have is the value of in this equation, whichever we have, a0 into k square minus n square, either a0 should be equals to 0 or k square minus n square should be equals to 0 from this equation. Are you able to understand? So either a0 should be equals to 0 or k square minus n square is equals to 0. But already we have seen that this a naught are not vanishing, therefore a naught is not equal to 0. So what we have to do is we have to make k square minus n square should equal to 0. So as the value of a naught is not equal to 0, we have to make k square minus n square should be equal to 0. So if you make k square minus n square is equal to 0, the values of k you are going to get as two values you are going to get. One value is k is equals to plus n, another value is k is equals to minus n you are going to get. Okay. So you are going to get two values of k, that is plus n as well as the minus n. These are the two values which we are going to be get. So therefore, this is okay. Next, what we have to do is, after getting the value of k is equals to plus or minus 1, now we will equate the coefficient of x to the power of k minus 1. This is the x to the power of k minus 1 to 0. So if you want to write x to the power of k minus 1, okay, k minus 1 if you want to write, then r value as 1, then we get this equation as a1 into k plus 1 whole square minus n square is equal to 0. Therefore, in this, k plus 1 whole square minus n square is not equal to 0. You have to remember. In the previous one here, a naught is not equal to 0. In this equation, k plus 1 whole square minus n square is not equal to 0. So therefore, you are going to, why it is not equal to 0? Because k value is having plus or minus 1. So therefore, this value, enter value is not equal to 0. We should get a1 is equal to 0. So that is what we have written here. a1 is equal to 0. So therefore, again after that, equating the coefficients of general term as x to the power of k minus r. Okay. The generalized term which we are going to get, write it as x to the power of k plus r. This is not k minus r. It should be k plus r. So if you are making the coefficient of x to the power of k plus r equals to 0, then what we are going to get is we will be getting in place of r plus 2 you are going to get. So in this equation, we are getting this one. Understand? So x to the power of a r plus 2 into k plus r plus 2 whole square minus n square plus r is equal to 0. So if you rearrange these, we are going to get this as ar plus 2, and this term we are going to get. So from this, we can write the ar plus 2 value as 1 minute. Next page. Right. So from this equation, we can write ar plus 2 value as ar by k plus r plus n plus 2, and this k plus r minus n plus 2, you are going to get this. This is the generalized term. Understand? This is the generalized term. So therefore, if you put a1 is equals to 0, that is already we know that since a1 value is 0. Therefore, we are going to get from this equation, what we are going to get is the values of a3, a5, a7, a9, that is the odd values of a9 and so on will be equals to 0. Right? K values, whichever we have got, two things we have got. Either k is equals to plus n, one condition we have got. Another condition is k is equals to minus n we have got. So first we'll take the condition k is equals to n we are going to take. So once if you take k is equals to n, and if you substitute in this equation, we are going to get it as ar plus 2 as this you are going to get. That is minus n plus r plus 2, r plus 2. What we did, k value we have substituted it as n. So we have got ar plus 2 is equals to this one. So again, if you take r value as 0, 2, 4, and so on, because a3, a5, a7, all the values are equal to becomes equals to 0. So we'll take only the even multiples of a we are going to take. That is r value we are going to take it as a 0, 2, 8, and so on. So from that we can get the values of a2 as this one we are going to get, and a4 as this one we are going to get, and similarly we can find out the value of a6 as this one, that is a0 by 2 to the power of 6, 3 factorial into n plus 1 into n plus 2 and n plus 3 you are going to get. So therefore, by substituting the value of k is equals to n, the values of a1, a2, a3 and so on. Okay, a1, a2, a3. So this one we have written only the even multiples by taking this a2, a4, a6 values we have got. So now we will write the values of a1, a2, 3 in this equation. Okay, in this equation, whichever we have written, first equation. Okay, this is in this equation. So if you write, so here we'll see where we are.
Sir, I have one basic question.
Wait. See here, in this page we have A2, A4, A6 values we have got, then we have to get the A1 values. So in order to get, we will substitute in this generalized equation, y is equals to. So in that if you substitute, we are going to get it as y is equals to A0 x power n, because already found out the values of these. So in that equation, if you substitute, we are going to get it as the values as this one. So this equation you are going to get y value, you are going to get as this one. So once after getting this y values, that is a0 x power n, because k is equal to, so we have taken as n, we have taken. So there we have x power k. So in place of n, we have to write x power n. A0 value already we have found, A2 value we have found, and A1 value we have got. All these values, if you substitute this, you are going to get. Right. So after writing this one, now you have to remember this equation. So this is that is the reason why yesterday I have briefly discussed about the gamma functions. Okay. So after getting this equation, y is equal to this equation, as we have seen yesterday's gamma functions. So in that gamma function, order n plus 1, we have seen yesterday, gamma of n plus 1 is equals to some integration of 0 to infinite, e to the power of minus x and x to the power of n. We have seen in the last class, we have seen about these gamma functions. So by taking that gamma functions, so here we have to write this. Gamma of n plus 1 is equal to n gamma n, which is equal to n factorial. And here we, 1 minute. So here we have this A0 is equals to this one, we can substitute. Okay, this is the Bessel solution. So here you may get bit confused, but if you go through the what we call gamma functions, you will be understanding properly. So this one, with the help of the gamma functions, we have written. So therefore, we can write Jn of x. Okay, so A0 value we can write as this one. Okay, An value, A0 value we can write it as this one, and y value whichever we have. So we will be writing here Jn of x, which is equals to x power n by 2 to the power of n gamma n plus 1. We are right, gamma of n plus 1. So because in this equation, we are substituting here gamma values. So then after we have 1 plus minus 1 whole to the power of x square, 2 square 1 factor. Inside whatever we have, that we are writing. Only this value we are writing in terms of gamma. Understand? This A0 value we are writing in terms of gamma function, that is 1 by 2 to the power of n gamma we have. So this equation we have got. So this one again we are taking out x power n and n factor 2 to the power of n gamma of n1. So this I'm getting sound. Please unmute yourself. Okay. So here we are writing this A0 in terms of gamma function. We have this equation. Right. So this equation summation of r is equal to 0 to infinite minus 1 whole to power. This entire equation we are writing as it is. We are writing. Therefore, summation of r is equal to infinite minus 1 whole to the power of r. We are rearranging this one into this one. This we are going to get it as a here x power n by 2 power n is there. So we can write this as x by 2 whole to the power of n. Here we have x to the power of 2r by 2 to the power of 2r. So this term, and this term, these two terms we can write it as x by 2 whole to the power of 2r minus n we can write. And the remaining here we have a gamma of n plus 1 as a gamma of n plus r plus 1 we can write here. Okay. So this is the condition by taking k is equal to n. Similarly, k is equal to minus n as this one. So that is j of minus n of x we are going to be getting. Okay. J of minus n of x. So we are going to get it as a, we have got two conditions. No, the value of k we have got plus or minus n. So first condition we have taken k is equal to plus n. We have got this equation. Next we have taken k is equal to minus n. This is the condition which we have got. So this is one we have. So which is similar to this one. So therefore the general solution of this Bessel's differential equation, we can write it as y is equals to a jn of x. Here x is missing. So here it should be x is equals to a jn of x plus b j minus n of x we have. So this a and b are two arbitrary constants we are going to call. Okay. So this a and b are two arbitrary constants we are going to be called. So this is what the general solution we have. And then after by taking certain gamma functions, these gamma functions, so we can write the value of jn, the values of jn of x, we can write it as this one. Right. So j of minus n of x is equal to this one we can write. So by substituting those, finally we can get it as this equation. Okay. So this equation jn of x we are going to get. So this equation order, this is what we have. D square by dx square plus 1 by x dy by dx plus 1. So the Bessel equation of order n is equal to 0. So initially we have. So there is another another method is there. Just you go through this one, which is similar to this one. So which we call it as the solution of this equation, whichever we have got Gn of x. So we can get with the help of the power series solution. So this is the power series solution. About the power, we'll get this as here you see. So here we get. So Bessel's equation of nth order is this one. Okay. So y is equals to a Jn of x plus b yn of x. So I'm not explaining all this because we won't have much time. So then we can write yn is equals to this one. This is the equation we can write here. So this is what we call it as a Bessel's function of second kind we are going to be called. We'll be calling it as Bessel's second kind we are going to be called here. So this is about the Bessel's differential equation. So these are the Bessel's differential equation, which is reducible equations. So you may not require this. So after this, we'll move to the generating function for Jn of x. Okay. So we'll move to the generating function of Jn of x. So we'll see this 1 minute. So here we have a generating function for Jn of x. As we have seen the generating function in the case of the Legenders also, Legender differential equation also. Here also we have the generating function for Jn of x. So this is a theorem which we have to prove e to the power of x. Here it has been written h minus 1 by h. In some books, the notation you are going to have, don't get confused. So the notation is different, that's all. So some books it has been written power of x.
Noise, please unmute.
Here we have e to the power of x h minus. Somebody's voice is.
I think it's
Somebody voice noise.
I think it's Jeenat.
Sir, Jineet Parvin. Who is that? They are not unmuted.
Wait. I am muting.
Jineet Parvin.
Yeah, I muted. So, okay. So unmute yourself. Right. So here we have the generating function. So this is the theorem. We have to prove this e to the power of x h minus 1 by h by 2 is equal to this. We have to prove summation of minus infinity to plus infinite hn. This is hn jn of x. Okay. So that we have to prove. Actually, it should be h to the power of n. It is not hn. It should be h to the power of n. This one. So you make correction. It should be h to the power of n. It is not h subscript n. It should be h to the power of n. Okay.
What is h, sir, here? Is it constant or something?
Yes.
What is h? What is the role of
this
h?
in this theorem? The value of h, h power n, it is nothing but the coefficient of h power n. We are going to get it as a Jn of x. So you see here we have. So
Voice is breaking.
N is a positive integer. Understand? Positive of h power n. It is not hn. It should be h power n. In this expansion, okay, in this expansion, e to the power of x into h minus 1 by h by 2, right? So in order to prove this one, what we have to take is we have to take e to the power of 1 minute here, e to the power of xh by 2. Okay, so this will be in the form of like binomial expansion, whichever we have. So e to the power of xh by 2 is equal to, we are getting it as a 1 plus xh by 2 plus 1 by 2 factorial xh by 2 whole square and so on, 1 by n factorial into xh by 2 whole power n. This is for positive power of xh by 2. Similarly, the exponential of minus, that is exponential of minus x by 2h. Okay, e to the power of minus x by 2h. So this we are going to get as this one. So one you are going to get alternate one, minus, plus and minus you are going to get. Final term we are going to get it as a minus 1 whole to the power of n into 1 by n factorial into x by 2h whole power n you are going to get. So therefore, here e to the power of x h minus 1 by h by 2 we can write it as this one. Understand? So if you add these two, this is the term which we are going to get. So this one we are going to get write it as e to the power of x h by 2, e to the power of minus x by h by 2. So already we have written the two term values, that is e to the power of x by h2 is this value, e to the power of minus x by 2h is this value. So we'll substitute here. So if you substitute and write, so this is the equation which we are going to be arise. Okay, this is the equation. So this is the first term, this is the second term, whichever we have. So therefore, after getting this equation, what we have to do is we have to take the coefficient of h power n in this entire equation. What we have to take? Coefficient of h power n we have to take. So if you take the coefficient of h power n, we are going to get this. So each and every one term, if you want to solve, we don't have that much sufficient time. So if you can solve this one. So we will take the coefficient of h power n in this product. So this is the equation which we are going to be get here. Okay. So after that, again, we have to take another coefficient of h power n we have to take. Okay, sorry. This should be h to the power of minus n. Already we have taken the coefficient of h power n. So it should be, you make a correction that some wrong is there here. You make the coefficient of h power minus n here. Okay, h to the power of minus n we have to take. So if you take the coefficient of h to the power of minus n, we are going to get this equation. This is the equation which we are going to get. So final equation is this one. Okay, so this is the equation we have. So once after getting this, the previous equation whichever we have, like by comparing by comparing the coefficient of h power n1, another one comparing the coefficient of h power minus n, we will get two equations we are going to get. So here h power minus n we have got this one, no? So by combining these, sorry, not comparing, by combining these two equations, okay, by combining these two equations, we are going to be get this one, okay, e to the power of x h minus 1 by h by 2. So this equation whichever we have, previously equation whichever we have. So this entire equation already we have seen that when we have solved the Bessel's differential equation, we have written it as Jn of x. So this one we have written. So by adding these, we can get it as a summation of minus infinite to plus infinite. Why we are getting minus infinite to plus infinite is in this equation, in this equation 2.15 we have the r is equal to 0 to infinite here. This one we have r is equal to 0 to infinite. So the limits will be changed to minus infinite to plus infinite. This is the equation we are going to get. So this is what we call it as a generating function we are going to be called. So just we have about this one. So we can expand this as this one. Okay. So this one e to the power of x h minus 1 by h by 2. Which we have is we can expand this one, and also we have another corner, second one. So this one, okay. So the coefficients of h power 0, this one, okay. Coefficients of h power 0 means the value of h power 0. If you take, so we are going to get 1 minus x square by 2 plus this we are going to get. So this is what about the generating function of this what we call Bessel's differential equation we have. Similarly, we have the recurrence relations. So these recurrence relations are very important. These recurrence relations frequently they'll ask in the short answer questions. Okay, so they'll ask in the short answer questions. So just we'll go through these recurrence relations here. So first recurrence relation which we have here is this one. That is what we have x. 1 minute. X Jn dash. Right. The first recurrence relation is x j dash n of x, which is equals to n jn of x minus, here it should be some, again, we have some mistake here. All of you note it down. This recurrence relation they have written wrong. So the recurrence relation is x j dash n of x is equals to n jn of x minus x jn plus 1. Here, 1 minute, I'll write here just so that you'll be getting. So here it should be x. X, it is not there. X. 1 minute. So here x should be there. X. Okay. So it is, the recurrence relation is x j dash n of x is equals to n jn of x minus x jn plus 1 of x. This is the recurrence relation which we have to get here. Okay, the first recurrence relation. These are very important in the short answer questions. So for that purpose, you see jn of x value we have written. So already we have got jn of x from the Bessel's function. That is the first order, otherwise first kind. What is we have is jn of x is equals to summation of r is equals to 1 minute. Summation of r is equals to 0 to infinite minus 1 whole to the power of r into 1 by r factorial into gamma of n plus r plus 1 into x by 2 whole to the power of n plus 2r. This one we have. So by taking this Bessel's differential equation of first kind, we will solve this first recurrence relation. So then what we are doing, we are differentiating this equation with respect to the x. This equation we are differentiating. So in place of j n of x, we are going to get it as a j dash n of x because we are differentiating. So summation of r is equal to 0 to infinite as it is, you are going to be get. And this minus this entire term minus 1 whole to the power of r, and this denominator we are going to get constant, and this we are going to be differentiate. This will be in the form of x to the power of n plus r. So it will be, what we are doing is we are going to get it as nx to the power of n minus 1. That is differentiation of x to the power of n is nx to the power of n minus 1. So n value is nothing but n plus 2r here, and x value is x by 2 and whole to the power of n plus 2r minus 1 we have, and the differentiation of x by 2 is 1 by 2. So this is what we differentiated this equation with respect to the x. Now what we are doing is we will multiply this equation by x on both sides. Okay, we'll multiply with x on both sides. 1 minute. I'll remove this. Right. So we are multiplying with x on both sides. So we are getting it as x into j dash n of x, and this total equation in this. So you see, in place of 1 by 2, we have written x by 2. The remaining all you have the same, minus 1 all to the power of r and n plus 2r by r factorial gamma function of n plus r plus 1. This entire you have same. Now again, this one we are rearranging. This equation we are rearranging. So how we are rearranging means simply we will divide, means we are adding these two. Okay. So summation of n is equals to this one, first term, r is equals to 0 to infinite minus 1 whole to the power of r, and this part we are writing. This part, 1 minute. See here, 1 minute. Only this part we are writing here. Initial case, this one. Okay, so this is what we have written, and we are writing this x by 2 whole to the power of n plus 2r. Here we are writing. Okay, and this x power minus 1 we are not taking. So n plus 2r and plus again the remaining part which we have is summation of r is equals to 0 to infinite and minus 1 whole to the power of r. This one r factorial gamma of n plus r plus 1, and this 2r we have written here. Means simply this n plus 2r term whichever we have been divided into two terms. This is the first term, this is the second term we have. Why we are dividing means this value whichever we have, okay, the value whichever we have, we are calling it as a jn of x, this one, Bessel's of function of first kind. So this entire thing we have written as Jn of x we have written, right? So this we have written it as Jn of x, that is n Jn of x we have been written. Plus the second term, again we are rearranging -1 whole to the power of r, and here -1 factorial, whichever we are going to get it as infinite. This one again with the help of the gamma function we have. 1 factorial is nothing but it is a -1 factorial is nothing but gamma function. With the help of gamma function, it is infinite. So therefore, we are writing r is equals to 1 to infinite. Here we are writing, okay, 1 to infinite, and this entire term we are writing. Now, what we are doing is we have to substitute r minus 1 is equals to s. We have to substitute r minus 1 is equals to s. So if you take r minus 1 is equals to s here in this equation, we are getting s factorial, and here we are getting it as a n plus s plus 2, because r is equals to what? S plus 1. So it is s plus 2 it becomes. Here also r is equals to s plus 1 it becomes. Here also n plus 2s minus you are going to get. Understand? So this we are going to get. So therefore, this equation we can write in this form, that is n Jn of x. Here minus x summation of s is equals to 0 to infinite. Okay. Here -1 s to the power of +1 we have that we have written as a -1 whole to the power of s, so that we are getting minus n here. This we are going to get. So therefore, this x j dash n of x is equal to, we have this term n j n of x minus x, this entire term, this one minute, this entire term from here to here, this part we can write it as a jn plus 1 of x. Jn of x is already we know, so simply we have written in place of n plus 1, that's all. So this is what x jn j dash n of x is equals to n jn of x minus x jn plus 1x we have. Okay, so this is the first recurrence relation which we have proved. Okay, so what is the recurrence relation we have been taken? Here it is. You see, this is the recurrence relation, no? This one, x j dash n of x is equals to n j n of x minus j n plus 1 of x. Okay, so here we have got that first recurrence relation. This one. Okay, this one we have got. So here we have got 2j, sorry, it should be, sorry, this one is another one, no? First recurrence relation is here. This one. This is the first recurrence relation we have got. Right. Similarly, we have second and third recurrence relation. There are 4 recurrence relations are there for what we call Bessel's differential equation. So second recurrence relation, you see, this one we have. What is the second recurrence relation we have is, we have to prove that x j dash n of x is equal, here it is minus, you may not be able to see, n minus 1 of x we have to prove. So in order to prove this equation, that is a second recurrence relation, again we are going to be take the Bessel's differential equation of first kind we have to take. So whatever we have equation is summation of r is equal to 0 to infinite -1 whole to the power of r, and so that is the first differential equation we have. So now again, as we have did the differentiation previously, same we are going to do the differentiation with respect to the x, and we'll get this equation if you differentiate with respect to the x. Again, both sides we have to multiply with x as we did in the previous one. So we have to multiply this. So after multiplying, we'll get this equation. Okay, so we'll get this equation. So here what we are doing is, here we are have -1 whole to the power of r into 2n plus r is there, no? 2n plus r is there. So here we are making that, here n whichever we have, we are writing it as a 2n minus n. 2n minus n is nothing but n only. So we are writing 2n plus 2r minus n, we are writing this same as it is. Now we will be writing this entire equation into two parts. So the first part is -1 whole to the power of into 2 into n plus r, this one, and the second part is -1 whole to the power of r into -n. This part we have been divided here. Okay, so therefore this one, whichever we have been divided here, this equation, we will be knowing from the here, this one. Okay, this one, Bessel's equation. So we write it as a Jn of x. Already n is there, so it is minus Jn of x. So therefore, here, after writing this, so this term we are going to get. So this term, whichever we are having, so we are writing in this form. Okay, x by 2 n minus 1 plus 2r we are going to write. So this one, whichever we have, so this is nothing but Jn minus 1 of x. This entire one. Okay, so this entire one. This entire one. Okay, so this one we have writing it as a Jn minus 1 of x. So here we have written Jn minus 1 of x. And x is there as it is. So it is x Jn minus 1 of x, and this is minus n Jn of x we have written. So this is the second recurrence relation which we have been proved. Okay, so similarly, we have one more. Third recurrence relation. 1 minute. I'm able to move. Right. So this is the third recurrence relation. This is 2j dash n of x is equals to njn of x and minus jn plus 1 of x we have to prove. That is the third recurrence relation which we have to prove here. So this third recurrence relation, simply how we are going to get is from the first recurrence relation we have this one, first recurrence relation, and this is the second recurrence relation. By adding these two, okay, so we are going to get this equation. So which is known as 2j dash n of x is equals to jn minus 1 of x minus jn plus 1 of x. This is the third recurrence relation which we have. Okay. So here, okay, no problem. Jn minus 1 of x into n. All right. So jn minus 1 of x. So we have to prove this one. So simply the values of jn of x and j dash n of x, sorry, jn of x we have to substitute here, because we have what we have by adding these two, we will getting this 2j dash n of x is equal to jn minus 1 of x plus, sorry, minus jn plus 1 of x. So in place of n, we will write n minus 1 and as well as n plus 1. So jn of x is this one, and 2j dash n of x, this one. So if you solve this, finally we'll get this one. So here, this equation we are going to get. After here, what they did is we have to take r is equals to s plus 1. Otherwise, r minus s is equals to 1 we have to take. So by taking this condition, we will get this one. This is the third recurrence relation we have. Okay. So similarly, the fourth recurrence relation, I'm not completely explaining this. So because already we have seen the first recurrence relation, second recurrence relation. So from that first and second recurrence relation, you may be getting this, because all the terms you are familiar with this. Okay. So then after we have a fourth recurrence relation. So this one we have to prove. What is the fourth recurrence relation we have? X, sorry, 2n jn of x is equals to x into jn minus 1 of x plus, so it should be sorry, plus here, it should be plus. Okay, so the fourth recurrence relation, it has been given minus here, it is wrong. Actually, we have to prove the fourth recurrence relation is 2n jn of x is equals to x into jn minus 1 of x plus jn plus 1 of x. Here it should be plus. You make it correction. So later on, if you're going through the notes, you may be getting confused. So here, actually, it is a plus, not a minus. Okay, it is a plus. Here it is a plus. Okay. So in order to prove this recurrence relation, already we have these two recurrence relations. That is x j dash n of x is equal to this value, and this x j dash n of x, we can write it as this one. Okay, minus n j n of x plus k j n of minus 1. So from these two equations, simply we will subtract 2 from 1, so that we'll get this one. Simple one, this one. Okay, this is a simple one you are going to get. So this one is the fourth recurrence relation we have. So alternate method, we have another method also. So in the another method means, so entire one. In the another method, we have to write all the j dash n of x and j n of x values we have to write. So this is the method we have. Okay, go through this. So this is what the different recurrence relation. Fifth recurrence relation is simply differentiation of these we have, that we have proof here. You go through this because each and every one means not. So we have completed the recurrence relations also. Next we have orthogonal properties of what we call Bessel's differential equations. As we have seen the orthogonal properties for Legender's differential equation also we have seen. Similarly, we have the orthogonal properties for what we call Bessel's differential. Last class we have seen orthogonal properties of Legender's differential equation we have seen. You have the orthogonal properties for the Bessel's functions also. So there are this is the theorem, we can say that orthogonal property. So here, what is that is? So here we have if alpha and beta are the roots of this equation, roots of the equation, Jn of mu is equals to 0. Next, the condition of orthogonality Bessel's function within the limits like a 0 to 1, within the limits from 0 to 1, this is the one equation. For alpha is not equal to 0, beta, and with the condition of normalization, this one we have. And similarly, both these equations represents the what we call a condition of orthogonality, and that can be written as in this form. Okay, and this single equation we can write. So again, we have something we have to remember about the Kronecker delta. Okay, so Kronecker delta, you are going to get this in the tensors you are going to get actually. So once if you finish the tensors, we will be knowing what is Kronecker delta. You will be knowing that Kronecker delta. So we have like a representation of the Kronecker delta is in this form. Delta of alpha beta, it is a Kronecker delta. So it will be equals to 1 in one condition, that if alpha is equals to beta, and this Kronecker delta value, delta of alpha beta will be equals to 0 for alpha is not equals to beta. So if alpha beta both are equal, then it will be equals to 1 Kronecker delta. If they are not equal, then it will be equals to 0. Okay. So in order to prove this orthogonal property, so we will take the Bessel's equation we will take. So already in the starting, we have seen what is the Bessel's differential equation. D square y by dx square plus 1 by x into dy by dx plus 1 minus n square by y, 1 minus n square by x square into y is equals to 0 we have. So this is the Bessel's differential equation. Now we'll consider the first kind of order n we have to consider. That is Bessel's functions of first kind of order we have to take. So what is the first kind we have is Jn of alpha x and Jn of beta x, which we call it as a u is equals to Jn of alpha x and v is equals to Jn of beta x we have. So by taking these two Bessel's functions of first kind of order n, we will substitute the values of alpha x for x and mu. Okay, we're substituting the alpha x for x and mu for y, u for y. So this is the Bessel's differential equation, no? D square y by dx square. in place of y, we are substituting the value of u. Okay, in place of y, we are substituting the value of u. So it is d square u by dx square. In place of x, we have alpha x. So it is alpha x square plus 1 by x, 1 by alpha x into dy in place of y u, and in place of x, it is alpha x plus 1 minus n square by alpha x whole square into u is equal to 0. So by rearranging, means by doing the differentiation here, rearranging, we are going to get, this is the final equation we are going to get. Similarly, for beta x and for v y, we are going to write. So in the Bessel's equations, the previous equation only, in place of beta x, we are going to write in place of x, and in place of y, we are going to write it as a v. Therefore, if you write, you will be getting in this form. We are not writing entire this one, only we are writing this part we are writing. So x square d square v by dx square plus x into dv by dx plus beta square x square minus n square into v is equals to 0. This is what we are going to get. Now, after writing that, we will multiplying this equation v by x and by u by x and subtracting. Okay. So first equation we are multiplying with v by x and u by x, and then we will be subtracting. So if you multiply with v by x to this equation, x square d square u by dx square into v by x, here you are going to get it as a v. Here x will get cancelled, so only it is going to be remain x into d square u by dx square into v. You are going to have, here we have this du by dx into v. You are going to get, here we will get another term, and again if you are multiplying this equation with u by x, so here also x will get cancelled. So finally we are going to subtract these equations. We are going to get this equation. Okay, this is the equation which we are going to get. So here d by dx into x, in place of this, whichever we have, okay, this one v, we are writing it as a jn of beta of x, and u jn of alpha x we are writing. Similarly here and here we are writing. So this is the equation which we are going to get finally. This is the equation, right? So this equation which we have is one orthogonal property. So then we'll get two what we call cases we are going to get. So like case one, what we are going to get is if alpha and beta are the roots of Jn of mu. This one, alpha and beta are the roots of the Jn of mu. So therefore, if they are roots, in place of mu, we will substitute alpha. In place of mu, we will substitute beta. So it will be Jn of alpha is equal to 0, Jn of beta is equal to 0. So by taking these conditions, Jn of alpha is equal to 0 and Jn of beta is equal to 0, and we'll be substituting in this equation. Okay. So in this, what happens means some terms, otherwise the first term of the equation, this one is going to be vanishes for these limits. So therefore, final equation which we are going to get is this one, alpha square minus beta square integration of Jn of alpha x, Jn of beta x, we are going to get this one. Okay. So again, as we know that alpha is not equal to beta, so therefore alpha is not equal to beta. Therefore, this equation we can write it as x Jn of alpha x, Jn of beta x. Only this Jn of alpha x, Jn of beta x. So if this is equal, they are not equal. So we are going to get this one is equal to 0. So this is the condition one we have got. And similarly, by taking the condition if alpha is equal to beta, okay, by taking this condition alpha is equal to beta, we are going to get this equation. Right. So this equation we are going to get. So by doing all these, we'll get this orthogonal property. So this is about the orthogonal property which we have. Basing upon these orthogonal properties, you have some examples. Just to go through this. Okay. So this is about the Bessel's differential equation. Okay. This is about the Bessel's differential equation. We have seen Bessel's differential equation, the solution for the Bessel differential equation we have seen. And similarly, we have seen the generating function and as well as the what we call recurrence formulas also we have seen. And then orthogonal properties we have seen. So on the orthogonal properties, So we have some examples, worked out examples. These you go through this one. Okay. So this is about a Bessel's differential equation. So these are some examples which we have. Right. So in the next class, what I'll do is just we'll go for another type of equations, which is a Hermite differential equations we have. Then we have the Laplace equation. So in the next class, we'll go through that one. Okay.
Sir, I have one doubt.
Yes.
Just wanted to understand the real-time use cases for this Bessel functions.
Just speak loudly. I didn't get you.
So can you hear me clear now? Hello.
Tell me.
What is the real-time use cases for this Bessel function, sir?
Bessel functions, all these we are going to be used in the form of what we call in this physics. I'll tell one application, 1 minute, where we are going to be used. This is in order to what we call in the waveguides, as well as this what we call rectangular waveguides, circular waveguides, we are going to be have. So there we are going to be use these. Okay. So these functions, whichever we are going to be study, all these like legenders or different legenders or Bessel's differential equations or Hermites, whichever we are going to be have, these will be utilized in what we call waveguides, as well as the rectangular waveguides, circular waveguides, whichever we are going to be have. So those application part you don't have in your syllabus actually. So if we put that also, it will be very lengthier. So that is the reason why they may not taken into the consideration. But we have some applications. Okay, in case of what we call vibrations of rectangular membrane, if you take all those, these are very useful, like oscillations of any hanging chain, all those. Okay. So these very useful in that one. So this differential equations where we are using means this is what we have. Okay. So even this after that you are going to study about the Laplace equations. So there those Laplace equations also we are going to use the case of the Cartesian coordinates, as well as the what we call a general cylindrical coordinates we are going to be used. Okay. So that is applications we have.
Okay.
So maybe what happens if you study these, you may be like mathematical only, but the maths we are going to be used in physics. Okay.
Okay, sir. I think it's a bit clear. Yeah.
So because of we have short times, I'm explaining very fastly because each and every one, if each and everything, if you want to cover, it is doesn't take means much time. It is going to be take. So we don't have much time to explain all these. Okay.
Okay.
So in the next class, we'll see two more like Hermite's polynomials, and as well as after that, we'll go for Laplace equations. Okay.
Sir.
Sure, sir. Thanks.
Morning, sir. Sir.
Yes. Tell me.
Sir, please tell some important questions, sir, for exam purpose. Yeah.
I'll tell later on. We'll be coming to the practical examination. Otherwise, I'll post some important questions in your group. Okay.
Okay. After finishing every chapter, then if you tell me, so we can read out notes.
Okay. After finishing black one, I'll give.
Okay.
Okay. After finishing black one.
Okay.
Otherwise, I have some previous year's question papers also. I'll post that. Not only using this Ambedkar University, we have like Usman University question papers also are there with me. I'll post those questions also. You go through that one. You're knowing that which question you are asking frequently.
Sir, please post in that group, sir.
Yeah. Should I post in the group or not?
Yes,
group,
sir.
Group, sir. Yes, sir.
Yeah, I'll post in the group. Okay. I'll post.
Okay.
Yes,
Okay.
Thank you.
Okay.
Thank you.
Okay, we'll stop here.
Okay, sir.
Thank you, sir. Thank you all. Bye.
అంటే వీడియో కాల్ కాదు మీ మీద అయితే చెయ్యొద్దు కానీ వీడియో కాల్